and immersive training where the learners can safely practice complex procedures again and again. But there's a catch. Most VR systems today are designed as static step-by-step tutorials, and everyone gets the same instructions in the same order, but regardless the learner's needs like different modality or pace. So that's the problem. And that's why we need adaptive VR systems. And adaptive systems have been explored in areas like cooking, surgery, and maintenance. But in manufacturing, where the psychomotor skills and precision matter, VR are still static. And so our question was, how does VR training that is adaptive, based on cognitive load, impact the learning in manufacturing? So that's when we had to achieve this vision, we had to build an end-to-end technical pipeline that combines sensing, machine learning, and VR adaptation. In this presentation, I'll walk you through the components. CLAd-VR has 3 main components, and the core is the interactive VR environment. It's a Unity-based simulation of a CNC drilling machine. Learners put on a MetaQuest 3 headset, and they go through modules and steps like Y setup, chuck setup, edge finding, and so on a 3-axis milling machine. So the environment has multimodal instructions like animations, text, diagrams, and videos. So the schematic diagrams provide the context. And all the user's actions, errors, or completion times are recorded in real time. But training is only half of the story. So while the user is training on the headset, the user also has an emotive Epoch X device. This device records the neural activity across 14 channels and at 128 Hz. So now comes the cognitive load sensing pipeline. So cognitive load is actually the mental effort we exert. And from the traditional cognitive load theory, it comprises of intrinsic load, which is from the task complexity, and the extraneous load from the poor design. So in VR environments, we must additionally account for technology-induced extraneous load. And our goal here is to minimize the extraneous and balance intrinsic and germane load. To sense the cognitive load in real time, the EEG signals from the emotive headset are streamed through lab streaming layer, which synchronizes them with the VR event logs. That is the task completion time, error metrics, task difficulty levels, etc. From these brain signals, we extract features like theta, alpha, beta, and theta to alpha ratio and spectral entropy. The next challenge was turning these raw signals into a meaningful state. So we ran a calibration phase where the user go through the phase and the baseline is at rest, and an easy 1-back task for low load patterns and a challenging 3-back task for a high load pattern are recorded. From these sessions, we established personalized thresholds for each individual's neural signatures, and then for classification, we implemented an LSTM neural network that learns how the EEG patterns evolve over the time. Every 2 seconds, the model processes a window of EEG data containing the band powers, theta to alpha ratios, and the spectral features from our 14 channels. The LSTM outputs a continuous cognitive value between 0 and 1, representing the probability of high cognitive load. We then apply these personalized thresholds during the calibration to classify this continuous output into discrete states like low load, optimal load, or high cognitive load. This approach allows us to maintain sensitivity to individual differences while providing clear adaptation triggers. The model processes data in under 100 milliseconds. While we use 2-second window for stability, this fast processing and continuous output lets us track the gradual changes in cognitive state and smoothly update the feedback. So, what happens when the system detects high cognitive load? It means that the learner is confused or stuck. And that's when we deploy scaffolding, also known as the adaptive feedback engine. So the system dynamically adapts feedback based on the learner's cognitive load. That is, if the user is having high cognitive load, then additional assistance is provided, and if it is low cognitive load, challenge is increased. So when the cognitive load is high and if the user doesn't know where to look, arrow cues highlight the right tool, and if they don't know how to perform a certain task, ghost hands demonstrate those steps. And voice guidance give them the explanation of why the step matters, and haptic feedback is given when the wrong tool is chosen while doing the task. And at the same time, if the system detects low cognitive load, which means the user is disengaged, so the approach is flipped. The task is made difficult by adding questions, like drill a hole at x, y coordinates. And time pressure is added for tasks simulating the real-world machining urgency. And sometimes the system injects an error, like a misaligned block, which the learner must catch and correct. And guidance is reduced, like instructions which are available are reduced. So by dynamically adjusting support and difficulty, CLAd-VR keeps the learner in the optimal learning zone, not overwhelmed, not bored, but actively engaged and learning effectively. So these are all the possible errors a user can make at each task and the corresponding feedback, adaptive feedback to be given. So this is one of our pilot testing sessions. On the right, you can see the VR view showing the task inside the headset. And on the left is the participant performing the activity in real life with the corresponding EEG readings on the bottom. So at this point, the user is trying to figure out how to insert the chuck key. You can notice a clear spike in the EEG readings when she's struggling to find the chuck key placement. So from our pilot testing, we noticed that users found some steps like edge finding are harder to perform, and that's exactly where the adaptive feedback is helpful. And the setup, the emotive and the VR headset induced some fatigue because participants wore both their headsets for about 30 minutes for the experiment. And what's interesting is that wherever we observe spikes in the cognitive load, those movements matched exactly with the points where the users were struggling. And that's when the adaptive feedback, additional assistance not only reduced stress, but also helped users finish their tasks smoothly. So of course, there are some limitations. The accuracy of EEG-only classification is limited to the active VR settings because the user movements and the muscle activity introduce noise that can mask real brain signals. This makes harder to reliably detect the cognitive load. Our dataset is still small and the adaptation logic is still rule-based, but we see these opportunities for future work as we expand our dataset, the accuracy would improve. And we're already planning to add multimodal signals like eye tracking and heart rate variability, so no single channel would carry all the weight. And also, we're planning to conduct user studies to test the skill transfer and retention. So the impact here is twofold. Trainees learn more efficiently and their skills are more likely to transfer back to the real manufacturing environment. To conclude, VR has already shown promise in workforce training, but to truly close the skills gap, VR systems must become adaptive. CLAD-VR demonstrates how a real-time EEG-based sensing and machine learning can transform static tutorials into intelligent training environments that respond to learners' mental state. Our goal is to create training systems that adapt like an expert instructor, knowing exactly when to step in and when to step back. Thank you, and I look forward for your thoughts.
Okay, due to the time limit, maybe a couple of questions from the audience. So, any questions? Okay, then my question is that you are training LSTM for EEG signal, right? But at the end, you said that there is a limit and you are going to introduce the multimodal. So can you say the detail of the limitation of the EEG signal only in this application?
Thank you for the question. So ideally for EEG signals, a lot of noise is added once the person is moving in the virtual environment. So we were using Emotive. Basically, Emotive has a movement artifact removal, but it doesn't account for the fact that we in the virtual environment would be making some hard adjustments with the drilling machine. So for now, we tested LSTM network because we needed the probability of high cognitive load towards the end. And when we introduce multimodality, we will probably go for some other architectures which decide which way to put on and how to figure out that probably the eye tracking or the gaze metrics are the reason for low or high cognitive load, or should we depend on just the EEG signals?
Yeah.
Just one comment, because Deshita couldn't make it. As you know, this year's travel arrangements are a little funky. But Deshita asked me to pass along the news that she's looking for 2 highly motivated PhD researchers and postdocs. So if you're about to finish your master's, or if you're about to finish your PhD, and you enjoyed this kind of work, so Deshita continues to work in kind of looking at complex psychomotor skills acquisition, cognitive load, multimodal, sensing plus AI plus skills training. So again, if that sounds like, obviously I'm biased because Deshita is a collaborator of mine, but if that sounds interesting to you, please reach out to her. She's on LinkedIn, or you can send her a line and CC me or something. But she's very creative. She's wonderful to work with. You could ask her students offline as well. But yes, do consider it.
She's amazing. Thank you.
Okay, then let's thank the speakers again with a big. Oh yeah.
I have a short question. Did you think about surrounding noise? So normally in a working situation, they might be placed next to other machines, and that would somehow influence the cognitive demand.
So ideally, we thought of that because in virtual reality, we can induce the noise and see like how it matters or hampers the cognitive load. We weren't able to carry out full-length user studies for now, so the next goal is to carry out user study and then introduce these things to basically mimic when a person goes into the real-time training environment. Yeah. Anything else?
Yeah.
One short question: how long does the calibration process take for the EEG?
So ideally, there are 2 steps. It totally takes 15 to 20 minutes, which is, I think, is a limitation because for every user we are training, it takes a lot of time. But
that's why I'm asking.
Yeah. So ideally, there are 2 steps. Emotive gives us the functionality to have the eyes open and eyes closed test, which defines the brain waves correctly. But when we plug in the virtual reality environment, we need to have that low and high value of each user to make it more personal. So we then carry out the 1-back and 3-back tests. So totally then amounts up to almost 15 minutes.
Okay. I'm sure you thought of this. Isn't it enough to just detect like increase or decrease in the signal, so you don't have to train or calibrate the model itself, but you just detect anomalies, whether it's rising or decreasing, to identify possible stress?
Yeah, that makes sense, but the thing is that inside the environment, it's a build-up process. So the person learns from each step and completes the step. So we adapted it accordingly to basically train on individual windows so that we can get, if the person is doing some errors, how is the EEG behaving?
Okay. I have no experience in EEG, so I'm just basic signal theory. Thank you.
Thanks.
Okay, then we applause for the speakers. Yeah.